Uh, Good afternoon. My name is Lytton Smith, and I'm Director of the Center for Integrative Learning here at SUNY Geneseo, and Associate Professor of English and Creative Writing. Welcome to the Jack 76 and Carol 76 Kramer Endowed Lectureship, the keynote event of this, the 15th annual Great Day celebration, Geneseo recognizing excellence, achievement, and talent. There are over 500 submissions from students that you can interact with via our virtual schedule all week and beyond. I'll place a link in the chat shortly, or you can visit geneseo.edu/great_day to interact with submissions. And we will shortly welcome this year's keynote speaker, Dr. Adam Frank, astrophysicist, for his talk, Light of the Stars, Seeing Climate Change in the Human Future in Our Universe Awash in Worlds. And we ask that you use the Q&A function to ask questions that can be answered at the end. Dr. Frank will be introduced in a moment by our cherished guests and college alums, Jack and Carol Kramer. And it is my great pleasure to introduce SUNY Geneseo's president, Dr. Denise A. Battles, to welcome them. An Oswego County native and a geologist whose career includes a deep commitment to science education and STEM gender equity issues, Dr. Battles has been president of SUNY Geneseo since 2015. President Battles.
Well, thank you so much, Professor Smith, for that kind introduction, and welcome everyone. Today does mark the 15th year that Geneseo recognizes excellence, achievement, and talent in all fields and in all forms from our creative, innovative, and intellectually curious students. And I'm very excited to be here to share and take part in this event. I want to recognize and thank those students for their impressive participation this year, as well as the faculty and staff and every member of our campus community and beyond who contributed to this event. This really is a campus-wide endeavor, and it only happens and it's only successful with everyone's keen participation. I'm so delighted to see that again this year, particularly given that we're doing this in a slightly different format than we have traditionally. Thank you all for being here today and for your participation in whatever form that takes. In one of Geneseo's most noteworthy programs. I am particularly pleased this year to introduce and acknowledge the generosity of two very special alumni, Jack and Carol Kramer, both graduates, as you've heard, of the class of 1976. In 2008, Jack and Carol established the Kramer Lecture Endowment, which provides funding for the Great Day keynote address that you're about to hear. This endowment exemplifies the leadership, passion, and dedication that infuses the Kramers' lives. Both Jack, who is Emeritus Chair of the Geneseo Foundation Board of Directors, and Carol, his equally engaged partner, approach life with a shared intensity and commitment to others. Geneseo is truly very fortunate to count them among our most enthusiastic supporters, and we're grateful to them for their consistent gifts of time, talent, and treasure to the benefit of their alma mater. They serve as models to our students, our alumni, and to our Geneseo community as a whole. And it is with much respect and admiration that I thank them for making this keynote address possible. And so here to introduce this year's keynote speaker, Adam Frank, are Jack and Carol Kramer. And I'll turn it over to them.
Thank you, President Battles. It's a privilege to be here, albeit virtually, to participate in Great Day and to introduce Dr. Frank. Great Day epitomizes the multidisciplinary and diverse nature of a Geneseo education. We're very pleased to lend our financial support to such a uniquely Geneseo event.
We'd like to tell you a short story that demonstrates the value of a Geneseo education. Let us introduce you to Emily, the lovely young lady with the electric smile in that photo. We met Emily 5 years ago on an Alaskan cruise where she was our scientific expedition leader. Our excursion started in Juneau with a visit to the Mendenhall Glacier before boarding our small 49-person passenger ship. We were chatting with Emily while we waited for our transportation to the ship. It went something like this.
So, Emily, did you grow up in Alaska?
No, I moved here 5 years ago after I graduated from college. I grew up in upstate New York.
You're kidding. Carol and I are from upstate New York. Where?
I lived in Fairport, a small town south of Rochester.
That's crazy. We lived about 5 miles north of Fairport in Penfield. So where did you go to college?
I went to Geneseo.
Holy cow, so did we. We're both Geneseo grads. So were you a geology major?
No,
Well, sorry, I assumed that because you know the topic so well. What science did you major in?
I was an international studies major.
International studies. So how did you end up as a scientific expedition leader?
Well, I've always loved the outdoors. My first job up here in Alaska was as a guide on a Denali hiking trip. A friend of mine told me about this opportunity and it sounded really interesting, so I called to find out the requirements. I studied the subjects on my own between my hiking trips and aced the test they gave me prior to my interview. I've been doing this for 3 years now and love it. I'm always learning something new.
Yeah. So as you can imagine, we became very good friends over the next week. You know, Geneseo bond is strong even when it's separated by several decades. We actually figured out that I was the Geneseo Foundation Board Chair when Emily graduated, and I had participated in her commencement. It's a very, very small world. Emily's story demonstrates that unlike many institutions' more narrowly focused curricula, a Geneseo education is so much more than just your major. And events like Great Day are a part of what makes that a reality.
Okay, speaking of Great Day, we better get on with our task. It's our pleasure to introduce today's keynote speaker, astrophysicist Dr. Adam Frank.
He is the Helen F. and Fred H. Gowan Professor at the University of Rochester's Department of Physics and Astronomy. Professor Frank is a leading expert on the final stages of evolution for stars like the sun. His computational research at the University of Rochester has developed advanced supercomputer tools for studying star formation and how they die.
Professor Frank's current work focuses on life in the universe and seeking the physical and chemical signatures that would indicate advanced technology on planets. In addition to his academic work, Professor Frank is interested in communicating science to a broader audience. He is committed to showing others the beauty and power of science and exploring the proper context of science and culture.
His most recent book, Light of the Stars, Alien Worlds and the Fate of the Earth, was a winner of the Phi Beta Kappa Award in Science in 2019. The book also received praise from the New York Times, NPR, and Scientific American. But Professor Frank has written 2 other books that address astrobiology and the concepts of time and the relationship between science and spirituality. He is co-founder of NPR's 13.7 Cosmos and Culture blog, and is a regular on-air science commentator for NPR's All Things Considered.
He also served as a science consultant for Marvel's Doctor Strange, and he has been featured on national and international science documentaries such as Alien Worlds on Netflix, Mars on National Geographic, and The Universe on the History Channel. The American Physics Society awarded Professor Frank the prestigious Joseph A. Burton Forum Award last year, which honors scientists for their impact on the broader culture.
He earned his bachelor's degree in physics from the University of Colorado at Boulder, and his master's and PhD in physics from the University of Washington in Seattle. He held a postdoctoral and visiting science positions at Leiden University and the University of Minnesota, where he was awarded the Hubble Fellowship in 1995. He joined the University of Rochester in 1996, where he received the NSF Career Award. Today is our pleasure to introduce Professor Adam Frank.
Well, thank you very much. It is a great pleasure to be here today. I'm so sorry we couldn't be here together. That would have been fun. It would have been lovely to meet everyone, but I'm really honored by the opportunity to speak at this really wonderful institution that this university has. Geneseo, it's interesting. We get a lot of our best students at the University of Rochester, our physics students from Geneseo. And I've actually had one of my PhD students was in fact a Geneseo graduate. So I feel a close connection to Geneseo. So today what I want to talk about is, I want to talk about a topic that I have been thinking about since I was a young man. So let me start, which is climate change. Climate change and and another topic I've been thinking about since I was a young man, which is life in the universe. So the title here is Light of the Stars, Alien Worlds and the Fate of the Earth, but it's really broader than this. I really would like to talk today about, 1 second, let me just make sure I'm started correctly. I just want to make sure I have everything set up. Yes, very good. Okay, so this topic is something I think that resonates deeply with what's going on right now. This has been the last 2 weeks in thinking about climate change. This has been a really interesting moment in perhaps maybe we are beginning to finally do something about climate change. So this is perhaps a timely moment to have this conversation with you. So my theme today is you can't solve a problem until you understand it, and you can't understand it until you can tell its story. So what is the story we're trying to tell? The human future on this planet. And in particular, there's a problem that we all know about, which is climate change, which can be defined as the anthropogenically, meaning human-driven, anthropogenically driven change in the planetary climate state. We have been in the Earth has been in a state for the last 10,000 years, which is characterized by the terms warm and moist, as opposed to ice ages, which are cold and dry. And we're changing, that's the way what the Earth has been, and now we're changing to something else. And the question is, what is that? Where are we headed? Now, along with climate change, there's also the question of resource depletion. So we are clearly going to be stressed in the future about freshwater, forests, biodiversity. All of these things are all of these topics are very much, sort of potentially existential dilemmas for human civilization. And it all kind of can be wrapped up into the term sustainability. We need to develop or transform what we have into a sustainable version of civilization. So that's the problem we know. But of course, this problem has run into politics. So I want to talk for a moment about science and politics. So what's interesting about climate change is that the increase in carbon dioxide and its effect on the climate, which is now so polarized, that issue is so polarized that pretty much, based on your voting patterns, that is going to determine your attitude about a scientific issue, which really doesn't care about politics. But what's interesting about this is as far back as 1965, climate change was already being addressed, or at least being recognized at the highest levels of government. So here's an address that President Lyndon Johnson gave to Congress in 1965, where he said, "This generation has altered the composition of the atmosphere on a global scale through radioactive materials," he was talking about nuclear testing, "and a steady increase in carbon dioxide from the burning of fossil fuels." 1965. So anybody who tells you that climate change is some kind of modern hoax that scientists have come up with in order to, increase their salaries or something, this is the answer to that. People already, the science at that point was already clear enough that there was a clear warning. But what has happened, of course? Well, there's been political polarization and denial, so that we get a large swath of the population which says the science is a hoax, you shouldn't believe in the science is wrong, all kinds of different reasons, which has become harder and harder to justify as the effects of climate change have become all the more important. So what I want to say is that, I started this idea of, well, you can't solve a problem until you can understand it. There's actually a deeper problem here. There's a deeper problem that more than just politics and polarization, the real problem is what we could call the Anthropocene. Now, some of you may have heard this term before, but if you haven't, I hope that I get to be the one to introduce it to you, because it's a really amazing idea. It's a stunning idea. Here is this picture is Earth at night, right? And you've got to realize the planet has been around for 4.5 billion years, and it's only like in the last 50 that at night it looks like this. If you'd visited the Earth any other time in those 4.5 billion years, the night side would have been dark. Other than some lightning, you wouldn't have been able to see anything at night. And now there it is, human civilization, mapped out across the globe based on where these lights are. And so what this picture indicates is how dramatic our impact on the planet has become. And in 2002, two scientists, Crutzen and Stromer, suggested that human activity had now become so dominant on the planet that it was now really the fundamental driver for how the Earth was operating. And they labeled this, they said, look, this is the beginning of a new geological epoch. And there's been lots of epochs before: the Holocene, the Neocene. I'm not even sure if that's a good one. I'm not like a geologist. But we have all these geological epochs, and they proposed the Anthropocene was the epoch we were entering into, in which human impacts would be the driving force for the planetary state. Now, the Anthropocene is really the thing we have to think about. It's that it's not just, human beings, burning too much fossil fuels or something. It's the fact that on the whole, we have reshaped the way the planet functions. So there was this very interesting paper from 2015, which defined the idea of that the way the Earth functions, the way the Earth has functioned for the last, say, 10,000 years, there are certain boundaries to how that system functions, and that we are pushing up against those boundaries. And these boundaries were not necessarily physical boundaries. They were boundaries in, say, how much phosphorus was being used on the planet, how much nitrogen was being used. And what they showed in this chart, we don't need to go through it in any detail, but they showed a number of different places where the functioning of the planet, think of the planet as being a giant engine, a giant machine, that we were sort of cranking up the, we were pressing on the accelerator to the point where the planet was getting to the point where the machine was going to have to start changing. It was going to shift its state. So for example, we move more mass around on the planet than natural processes. Nitrogen, we move more nitrogen around than all natural processes put together. Phosphorus, we move more, which is a key element for life. We move more phosphorus around than all natural processes put together. And there was a number, they listed a number of these boundaries for how the planet operate, and how we were pretty much, a number of them, we were right up to the edge, where if we pushed any further, the planet was going to have to shift to a new state, that the planet was going to leave the state we found it in when civilization began and switch to a new state. So it's based on that idea. I want to think with you about the idea of the Anthropocene, which is really what's happening. It's not just climate change. It's this fundamental shift in how the planet operates because of us. And I want to look at that question, not in terms of politics, not in terms of questions of capitalism versus socialism or business versus ecological movements, but in terms of another new term, astrobiology. So what I want us to look at this problem from what I would call the 10,000 light year view. So, okay, what is astrobiology? And in particular, I want to talk about astrobiology, and I want to point out the fact that there have been three profound revolutions in the study of astrobiology over the last 30 years, which completely change our understanding of life in the universe. So what is astrobiology? It's basically the study of life in its astronomical context. Mainly that means its planetary context, but we want to think about things like how, when the star changes, how does that change the possibilities for life or the evolution of life? How does the impact of what's happening with other planets in terms of Jupiter kicking around comets, which will rain down on Earth, which has happened? How does that change the possibility and evolution of life? So it's always thinking about life in a broader context than just some sort of green scruff on the surface of the Earth. Now you might say, hey, wait a minute, we only know about one example of life. So, how can you study astrobiology when you've only got one example? Well, that's true. However, as I'd like to show you, these revolutions that have occurred have really enriched our understanding of how to set the context for thinking about life in planets. So let's go through these three revolutions, and we're going to talk about them in detail. So let me just list them first. The first is the discovery of planets orbiting other stars. The second is the exploration of our own solar system and all the planets in our own solar system. And the third is the exploration of Earth's 4.5 billion year past. Okay, so those are the three revolutions. Now let's talk about why they shaped things. So the interesting thing about planets orbiting other stars is that you can see people arguing about this as far back as the Greeks, right? You can see Aristotle and Democritus yelling at each other about whether or not the stars in the night sky had other planets, just like the sun had planets orbiting around it. Well, of course, people didn't, Aristotle and Democritus would have argued about whether or not the planets were orbiting around the sun or the sun was orbiting around the Earth, but we can ignore that for a moment. Right now, the question is other stars. Do other stars have planets? So for 2,500 years, people are arguing about this. And then in 1995, we definitively answer the question. How often does that happen? That a question that's 2 millennia old gets definitively answered. And we now know, this is amazing, Every star you see in the night sky, every one you look at, has a family of planets orbiting around it. That is stunning. The universe is awash in planets. And if you look at those stars and you count up 5 of them, 3 of them will most likely have, 2 of them will most likely have worlds in the right place for life to form, okay? So that's a lot of worlds. So it's not just planets, it's planets in the right place for life to form, meaning you can have liquid water on the surface. That's a lot of planets, okay? And we're gonna talk about how many planets that actually turns out to be. So that was revolution number 1, because now we know about all of these planets that are potentially habitable. Here's just a short list or image of all. Now these are, of course, most of these are artists rendering, but we know where these planets are and we can point telescopes at them and get data from them. And in the future, as our telescopes get better, we're going to be able to test whether or not they have life on them or not. We're going to have indirect tests for the possibilities of life on them. Revolution number 2 was the study of our own solar system. So look at this picture. This looks like this could be Tunisia or a desert in the American Southwest, but it's not. It's Mars, right? Mars now is the only planet in the solar system entirely inhabited by robots, right? They're all of our robots. In fact, most of them are American robots, as a matter of fact. But we've had robots trundling around Mars now for a couple of decades, and we've learned amazing things about the planet. In particular, we've learned that Mars was once a blue world. There was a period when Mars had large amounts of water on its surface, probably about 4 billion years ago. And in a stunning example of climate change, the climate changed, and Mars now is a frozen, dry desert planet. But we know a lot about Mars. We know a lot about Venus. We know a lot about Titan, which is this incredible moon of Saturn that has an atmosphere. We now have studied climate on all of these worlds. We understand how climate functions in a very deep way. And Mars, perhaps, there's a number of these worlds that still could have life on them, even if it's microbial life. So our understanding of life and planets, we have all of these examples on the solar system that we have now studied in quite a bit of detail, and we'll study more, that give us hints and understanding about how life and planets can evolve together. Okay, for the third revolution, I would like you to look at this picture and tell me which one of these is Earth. So I'll give you a second to think about it. Ding. Now, some of you may have guessed the answer, but many will say, oh, it's that blue one in the lower middle row, or the middle of the lower row. But in fact, these are all Earth. As we go back through Earth's 4.5 billion year history, the Earth has been all of these worlds. So going from left to right, top to bottom, that red one at the top, this is what the Earth looked like right after its formation. It was a lava world as it was being constantly impacted by comets from outer space. And then later on, the oceans formed, and it was a water world. There were really no continents. There were like maybe a few Australia-sized bodies, but it was mainly an ocean world. And then continents grew, but at periods the Earth was so hot that there was light. It was a jungle world. There was lots of vegetation, but the temperatures were so high that there was virtually no ice on the planet. And at other points, there was ice everywhere. The Earth was a snowball world, almost entirely glaciated from pole to equator. And then, of course, here's the lovely version we have now. And in another billion years or so, the sun will warm up to the point where the oceans will boil away, and the Earth will be, an uninhabitable world. So these are all the Earth, and we know about all these different Earths because we have our scientific techniques give us a view to the last 4.5 billion years. So we've really been able to map out here all of the different epochs, all the different eras, all the changes in Earth's history. And that gives us a huge view. It tells us how life can change a planet and how a planet can change life over long periods of time. And what it's shown us is that when we think about the Earth, we have to think about a set of coupled systems. The Earth, we should think about the coupled planetary systems that are the Earth. And that is the atmosphere, all the gases, the hydrosphere, all the liquid water in all of its forms, the cryosphere, all the ice, the geosphere, which is the rocky part of the planet, and then the biosphere, which is all of the life. All of these are each a separate system, but they're all strongly coupled together. And if we want to understand what's happening in the Anthropocene, we have to think in terms of the coupled Earth systems. And if we want to think about life more generally, if we want to do astrobiology, we have to think about how these coupled systems might fit together on other worlds in other conditions. Now this image here, I really love this image because it's sort of, it's a nice schematic of all the different eras of Earth's life, going all the way back from the Archaean 2.5 billion years ago, or actually longer, but all the way up to now. And now, the last 10,000 years have been a period called the Holocene. And I want to focus on that for a minute because it's important for us. So all hail the Holocene. The entirety of human civilization fits into the geological epoch we call the Holocene. So that's the last 10,000 years. So to get an understanding of what the Holocene is about, let's look at this map of global average temperature relative to the temperature for the last 100 years or so. So you can see this line starting back at 450,000 years ago. You can see this blue line. It's -6 degrees from the average temperature now. That's pretty cold when you think it's the whole planet. And then it goes up and it kind of pops up above the average, and then it goes down again for a long time, and then it pops up again, and it keeps doing this, right? These are the ice ages. Every time the temperature is very low, a good chunk of the Earth is swathed in ice. And you can see this down here with the ice volume, right? So you can see that every time the temperature is low, you got a huge amount of ice volume. And every time the temperature peaks above 0 here, which is above the average we have now, the ice goes away. So you want to know what human history is? Human history is right there. And by history, what I mean is the advent of farming, right? Once we domesticated ourselves and started to build villages, and the villages became cities, and the cities became empires, all of that. That all fits into right here. Okay, the whole of human history has been in this relatively stable, right? The temperature hasn't fluctuated very much, maybe 1.5 degrees up or 1.5 degrees down below the average, but it's been pretty stable. And all of our history fits into this relatively moist, warm, lovely time for having agriculture and building a civilization, right? And now the point of this is to understand, and now what's happening is, if we go here, if we actually looked at the temperature in detail here, we'd see that the temperature is now starting to skyrocket, right? That's the Anthropocene. So you can't really see it here, it's not mapped on here, but the temperature is now starting to rise to the points where, above where could get even higher than than what this was back then. So it's human beings, it's life, which is changing the planet. But now that's not actually that unusual. So I want to take you back to about 3 billion years ago. And I would like to ask you to, imagine your spaceship landing on the Earth 3 billion years ago. Now, if you landed, you'd find something like this, nice blue sky, oceans. Now this is life. These are these algal mats that would have covered a lot of the intertidal region. So it was a living planet, rich in life. So I would like to ask you, what would happen if you opened the door and stepped out of your spaceship? What would be the first thing that would happen? And the answer is you'd die. And you would die because there was no oxygen in the atmosphere. Beautiful planet, beautiful atmosphere, just no oxygen. Where did the oxygen come from that we're now breathing? Why was there no oxygen then and suddenly now there is oxygen? And the answer to that is life. There is something called the Great Oxidation Event, which happened about 2.5 billion years ago. And it was the result of life figuring out how to do photosynthesis by using water. And the byproduct of that was, in some sense, pardon my language, farting out oxygen. So it was all of this cyanobacteria, which was respirating out, breathing out oxygen as part of its life processes that eventually filled the atmosphere with oxygen. So if you look here, this is a plot of oxygen level in log scale going back in time. And what you can see is, 3 billion years ago, there was less than 1/1,000,000th of the amount of oxygen that we have in the atmosphere now. And then somewhere around 2.5 billion years ago, it climbed pretty rapidly and then climbed again less than 1 billion years ago. And it's all because of life. I mean, now what was happening is there was complex interactions going on between life and the geosphere. It took a while for the planet to absorb the rocks, et cetera, in the ocean to absorb a lot of this oxygen, and then the atmosphere could pick it up. But this was the main point here, was that it was life. It was life that fundamentally change the atmosphere of the planet. Does that sound familiar? Right? That's what we're doing now. So for people who say like, oh my God, it's impossible, we could never have changed the climate, we could never change the atmosphere, we're not powerful enough. Oh, yes, we are. And this is not the first time it's happened. The planet and the planet and the life have been co-evolving for quite a while. And this leads us to a very interesting idea that was proposed in the 70s, something called the Gaia Hypothesis, which some people may be familiar with. And it was an idea proposed by a physical chemist named James Lovelock, and was collaborating with the biologist Lynn Margulis. And the idea was that all living things on Earth, the biosphere, kind of function as a superorganism that has the ability to change the conditions in its environment to regulate the planet, to keep the planet habitable for life. So it's, in some sense, the life has hijacked the Earth and controls, not in a conscious way, but controls the physical conditions on the planet through feedback loops to keep the planet's temperature, et cetera, in a place that's good for life. So this was really a radical idea at the time. And when it came out, scientists really hated it. And first of all, this is Margulis and Lovelock. That's Lynn Margulis and James Lovelock here in front of a statue of Gaia that was on his land. And this was a seminal, brilliant idea. But when it came out, scientists were against it. A lot of them were. And the reason why they were against it was because of these two. This is Oberon and Morning Glory Zell Ravenheart. And they were literally priests of Gaia. What happened was when Gaia came out, right, it was such a groovy idea that scientists hated it, but they hated it because people loved it. People loved the idea of that kind of Earth Mother. And there were, people would have Gaia concerts and Gaia Earth Love festivals. And so, there literally was a church of Gaia that Oberon and Morning Glory Zell Ravenheart were priests of. And yes, that is a unicorn there, right? That is actually a unicorn, which says a lot. Now, listen, I'm sure these were very nice people. I don't mean to make fun of them, but the idea was that it seemed so new age and earthy, crunchy, groovy, and hippie that scientists were like, there's no science in this. And in particular, what science objected to was the idea of teleology, right? Teleology means a goal. And of course, the idea behind evolution is there's no goal. Evolution is blind. So scientists sort of pushed back on the idea that the Earth but the life wants something from the Earth. So what happened is there was a pushback. But really, people recognized after a while that the most important idea here that came out of Gaia was the idea that the biosphere is a dominant player in the history of the Earth. That part stuck, and so rather than use Gaia, people started talking about Earth system science. That's the term that everybody uses. And so the idea of coevolution, that the life and the planet were co-evolving together, became a dominant idea. And so I won't go through this, but this sense that the planet changes and life changes with it, but then life changes, evolves, and then it takes the planet with it, like the Great Oxidation event. That's kind of things like that have happened multiple times. So you do have to kind of consider life and the planet as a whole. And that's going to be a very important view for us as we think about what's happening with us right now with the Anthropocene. So the astrobiological question that we get to when we want to think about the Anthropocene I can frame it this way, right? We all know we have to build a sustainable version of our civilization. But the question is, does nature do that? Right? Is there such a thing as a long-term sustainable version of an energy-intensive civilization like our own? So, we know that the universe makes comets. We know that the universe makes black holes, et cetera, but we don't know whether there's even such a thing as a long-term sustainable energy-intensive civilization. So this is why I think, thinking about the problem from an astrobiological point of view, is this something that planets and life do in general is a very useful way to address the problem. And because it's going to fundamentally alter the way we come at it, the way we think about the problem. And I think it can free us from some of the ways in which we're stuck in dealing with the problem now. So the goal in my research has been to develop an astrobiological perspective on the Anthropocene that can inform new perspectives on the trajectories, the path that any civilization would take going into and getting through its Anthropocene to become a long-term sustainable civilization. So let's look at what the specific questions you could ask if you take this perspective. So one is, how common are they, right? If there are other examples of civilizations in the universe, and we're going to talk about that, how often do they hit an Anthropocene? Do they all have to pass through an Anthropocene, or is it very rare? How fatal are they, right? Does every civilization that hits an Anthropocene, that's it, that's the end? Or do, some number of them make it through? This question can be framed in terms of what is the average lifetime of a technological civilization? Is it, basically we've been technological for about, or industrial for about 200 years, right? Do we get, is that it? Are we going to get maybe another few hundred years? Or are we going to get another million years? So this is an important question, as we'll see. And then this is really important. If you make it to become a sustainable long-term version of a technological civilization, what properties does your planet have, right? If I look at it, just the planet, from a distance, how does that planet look different from planets that don't have a technological civilization? So I figure out the elements that you need to become long-term sustainable, and then aim my policies and my ideas about civilizations and planets in that direction. Okay, so if we're going to think this way, if we're going to take this long-term 10,000 light year view, the most important part is that we have to take exo-civilizations, as I've called them, i.e. aliens, seriously, right? We're going to have to really think like, hey, we're going to have to, there could be, or there likely were other civilizations, or are other civilizations, so that, we just become one of a statistical sample. So I don't want to take them seriously in terms of detection. That's important though, and I'm working on that, actually looking for technological civilizations in the universe. I'm not going to ask about their biology, because I really can't answer that question. There's no, the rules of physics and chemistry and even biology don't let me answer whether or not they're going to have 5 hands or 2 hands. That's beyond really what I can answer. Certainly, I can't say anything about their sociology, right? If I want to do a science of the possibilities of civilizations, I'm limited by the universal principles I have at my disposal that I can deploy in asking these questions. So sociology, like, whether they're capitalist or communist, forget it. That's just not going to happen. There's no way to do that. What I can do, though, is I can focus on coevolution. I can focus on a civilization plus the other coupled planetary systems. That's a problem that's really about, chemistry and physics and energy flows. I don't really have to know anything about the civilization, like, how many sexes they have, to really answer this question about how the civilization and the planet can evolve together. So I might be able to do some science here based on what I already know about planets and how they function. But of course, the most important thing that's keeping us from thinking about alien civilizations is what I call the giggle factor. It's prosthetic foreheads, right? We have had 60 years of bad science fiction TV where the aliens always have giant prosthetic foreheads, and so it's the giggle factor. We got to get over that. We're getting to the point now in our understanding of life and the universe where we got to get past the giggle factor. When anybody mentions alien civilizations, we need to get past going like, and a lot of that's because of UFOs, the silliness around UFOs, etc. But we really, we can talk about in the questions, we are poised now in the next 10, 20 years to have real data about life in the universe. Now, it may not be about civilizations, but certainly life, the first step on that. We're going to have data relevant to that question. So it's time to get past sort of the giggling, though I understand the giggling. Okay, so ask me, if somebody wants to ask, the search for techno-signatures or search for signals for life in the universe, civilizations, ask me about it, because it'll be fun to talk about in the questions. So, all right, I just want to spend a little bit of time now talking about the work I've done trying to get a science of exo-civilizations. Now, of course, this all has to be theoretical right now, but theory is very powerful. Before any of before any airplane you've ever flown in has been built, there's been a lot of theory, a lot of simulations that are done before it's constructed. So, theory is pretty potent, and so it can show us some things. All right, the first thing we want to know about is whether or not there's the possibility of exo-civilizations. And if we go through history, this has always been a battle between optimists who are like, oh yeah, absolutely. There's so many stars in the sky. Of course there's life. And pessimists who are like, no, you need, there's just not enough, the odds are so low that you run out of stars and planets before you find another one. So let's just talk about that for a minute. And to talk about it, we have to talk about what's called the Drake equation. And this was a very famous way of sort of setting out the problem that Frank Drake put together about 50 years ago. And it's guided our thinking about astronomy or life ever since. And it basically said, look, the number of civilizations in the galaxy will be a product of the number of stars in the sky, the fraction of those stars that has planets, the number of planets that are in the right place for life to form, meaning where liquid water can form, and then the fraction of those planets that evolve life, the fraction of that life that becomes intelligent, the fraction of those intelligent life that develops civilizations, and then what I like to call the final factor, the lifetime of the civilizations, right? We've already encountered that. Now, we don't need to spend a lot of time in this. I just wanted to show you that you can break that big question of how many civilizations there are into these sub-problems. Each one of these factors is really a sub-problem you could ask. And when Frank Drake proposed this, the only term here that was known was this, F sub star, or R sub star, the star formation rate, or another way of looking at the number of stars in the sky. But since then, we now know for sure, because of the exoplanet revolution, 2 more terms. We now know what the fraction of stars that have planets is. 1, every star has a planet, or at least one planet. And we know this, how many, on average, how many Earth-like planets there are in around a star. And this turns out to be like, 2/5 or so. Which means you got to count up 5 stars, and you'll get two that have Earth-like planets. But the point is, we now know all of these terms, and by knowing all of these terms, I can kind of play with this, and I can find the probability that, or at least I can find a limit on the probability that Earth is the only time it's ever happened, the only time that there's ever been a civilization, right? So what I do is I take this equation, I feed in the fact that I know this number and that number. So that's F of P of 1, N of E is a 1/5, excuse me. And then what I can do is I can play with this equation, and what I find out is that they're basically, in the universe, in the observable universe, there are 10 to the 22, which is 10 billion trillion planets where life could form. That means there have been 10 to the 20, there are 10 to the 22 experiments that nature has run on life and civilizations, right? So the only time it's ever happened is if the probability per habitable zone planet is less than 1 in 10 to the minus 22, right? That's a pretty small number. If it's, if it's a little bit above that, then we're not the first time it's happened. It has happened before. So even if, for example, even if the odds, of getting a civilization were 1 in a million, which is pretty low on planets, you would still have billions of civilizations that already existed. So, the exoplanet revolution gives us a unique perspective now that shows us that we're probably not the only time this has happened, which means the question of have there been other Anthropocenes can be asked, right? It's a meaningful question. So unless the universe is really biased against making civilizations, unless somehow physics and chemistry and evolution really, put up a wall against civilizations, we're not the first time it's happened. Okay, so I wrote this for the New York Times, and I wrote this research up. I did an op-ed off the Times, and they titled it, "Yes, There Have Been Aliens." Now, I wouldn't have put it that way. I would have said, yes, there probably have been aliens, because it's all probabilistic. But that would not have made as much fun for a headline. Okay, so the conclusion here is the Anthropocene. There has at least been the possibility of the Anthropocene happening before, because you've had civilizations before. Now let's see if we can ask the question of whether or not Anthropocenes happen, and do civilizations get through it? And how we're going to answer that is by doing some modeling. We're going to model the interaction between a civilization and a planet over long terms. And we'll run the model zillions of times and see what comes out. So I call this jokingly the theoretical archaeology of exo-civilizations. It's as if we could go out and go through all of space and look for every planet that ever developed a civilization and see what their fates were, what their histories were. Now, how do you do this? Well, what we're going to do is we're going to use math. We're going to use what's called dynamical systems theory, which is a very well understood method for understanding how populations and the environment interact. So for example, there's something called the predator-prey model, where you model mathematically the interaction between, say, a bunch of bunnies and a bunch of wolves. And the equations tell you like how often the bunnies multiply, and then it tells you how often the wolves multiply, and then it tells you how often the wolves find the bunnies. And I won't go into this in detail, but it basically shows this oscillation. The bunny population goes up, and then there's lots of bunnies for the wolves to catch, and then the wolves catch them and the population goes down. And it shows these oscillations in the population level, which very well matches what we see out in the wilderness, or even in a petri dish when we have microbes. So this is, this kind of modeling is very well established. And so what we did is, in a paper, we tried to model the interaction between a civilization and a planet, where the civilization was using the planet's resources, just like we are, and the planet was responding to those the use of those resources by changing the climate state. And so this was actually, I wrote this up for the Atlantic, and people were really interested in this, because in some sense we were saying, what can happen? We were modeling what can happen on other worlds. So I don't ask you to know these equations. I just need to show you that the equation. So this is sort of like my guns, right? You always have to show some equations just to be impressive. I will note that actually it was my students who solved these equations, including some undergraduates. Very important for you undergraduates. They were able to do the computer modeling to get this to work. And basically we had an equation for the population of the civilization and an equation basically for the planet temperature. And and interestingly enough, we took these equations from some researchers who had studied Easter Island. So Easter Island is this isolated Pacific island where that had been inhabited, had a huge human population, and then they just disappeared. And it's modeled that one of the reasons they disappeared is that they basically used up all the resources on the island, and then there was nowhere to escape. They cut down all the trees, and they couldn't even escape the island in canoes. So kind of an interesting idea, right? Because in some sense, that's what we're talking about. Whether Earth is an island, and we're using the resources, and we're changing, the Earth's resources, and we're changing the planet, and then at the same time, the planet will change us. Okay, so here's a bunch of results from our models, where the green shows the population and the red shows the planetary temperature. And this is time going along here, right? So we ran the models lots of times, and we found that we had certain classes of behavior. So let me show you what these were. The first kind of class of behavior in the models was what we call die-off. So let's look at this model over here. You see the green. Green is population. We turned on the models, and the population started using the planet's resources, and its numbers shot way up. There was just this rapid expansion in the population until the population got so high that the planet's temperature started responding. As the planet's temperature rose, it made it harder for the population, the civilization, to survive, and you had a big die-off. The civilization lost half or more of its population, which doesn't necessarily mean the end of the civilization, but it would be pretty stressful. We already saw with climate change, with the pandemic, what happened when we lost started losing a fraction of our population. If we were to lose 7 out of every 10 people, would civilization hold together or not? I don't know. Okay, but that was one class of model. The other class of model we found was a sustainable model, where the population rose, the temperature rose, but then you see it just leveled off. Like it was like a smooth landing. So the population had grown, but they had come to the population and the planet had come to a nice equilibrium. And what's interesting about this is it answers the question that I originally posed. Are sustainable civilizations even possible? The answer here is, yeah, they are possible. These models, at least, show that you can have sustainable trajectories. So that was good news. And it's funny because in the news, we got a lot of press for this, and everybody wanted to focus on the die-offs, right? Or with the next version, the collapse. But nobody really wanted to say like, hey, we actually found it's possible. That's good news. Okay, so the third class is what we call collapse, which is where the population rises, the temperature rises, and then you get into a dangerous runaway effect on the planet, where the temperature just keeps rising so much that the population can't sustain, and it comes down like a stone. Okay, so the models were successful in showing us possible routes of behavior for Anthropocenes as a general general kind of interaction between a planet and a civilization. Okay, I'm going to skip this next part in the for the sake of time. This was really just to note, and people can ask me questions about later, what are the sustainable characteristics, or sorry, what are the planetary characteristics of sustainable worlds? What does, if you make it to a sustainable world, are there things about it that are recognizably different from a world without a technological civilization that's sustainable, that, you know, we can identify and might be useful? So I won't go into that now because it'll take too much time, but we can talk about it in the questions if we want. So in the last 5 or 10 minutes, what I want to sort of stress is, now that we've sort of taken the first steps in developing an astrobiology of the Anthropocene, how does this perspective change how we view ourselves, right? That's really the most important thing. Because I've been writing about climate change for a long time, and I watched with horror the rise of climate denial, the rise of organized, widespread climate denial, which then became general science denial, like with the vaccines, et cetera, and then just became reality denial with things like elections and such. But for me, it really started with science. Once people started denying the basic results of science, that sort of opened the door just to say, like, well, there is no truth, right? So I believe that the astrobiological perspective shifts the way we talk about climate change in a way that can be very, very useful. Okay, so the first thing that shifts is the Earth will be just fine, thank you very much, right? A lot of times when we talk about climate change, we talk about it as if the Earth was like a furry bunny that we had to protect, right? Like, oh, the little Earth, oh, I hope the Earth's gonna be okay. That's a clear misunderstanding of what the planet is, right? This is not a battle to save the planet. For example, we are triggering probably a mass extinction right now. And there's been 5 known mass extinctions that have already occurred. But what happened was, on the planetary scale, was that each of those extinctions opened up a niche for the next set of species to evolve. So for example, this is your great ancestor, you know? This is the Zoodon, Zoastrodon. It's a Jurassic mammal. It's one of the early mammals, and you are descended from this. And the only reason you're here is because of the mass extinction that wiped out the dinosaurs. So the Earth's going to rebound. It's not about the Earth; it's about us in one sense. So what this raises a really profound philosophical question, which is, what are we trying to sustain exactly, and what responsibilities does that lead us to when we think about the Earth and our relations to it? So what are we trying to sustain, and what moral imperatives do we invoke to sustain that? So for example, we often see pictures of polar bears when we think about climate change, and polar bears on lonely ice floes, because polar bears are endangered. And what's interesting about this to me always is that polar bears are apex predators that would, be very happy to hunt you down and, eat you. But whatever, they're furry and they are adorable. And so, they're megafauna that trigger a reaction in us. So we care about their extinction, right? But what about this guy? Nobody's crying for the velociraptor, right? There were lots of velociraptors around and they're gone now. So, extinctions are part of Earth's history. And so what is it that we are trying to do when we think about what we're trying to sustain? Now, let me be clear, because sometimes people get angry with me in this, and you'll see where I'm going with this, I hope. In no way a climate change poses an imminent and probably existential threat to the project of civilization. And we have to deal with it in an initiated, coordinated way, like last decade. We're late on this. What I'm going to be leading us to is I believe the way we talk about it, climate change, has actually thwarted our efforts to make progress in terms of marshaling collective action, right? So, I wrote this piece for the New York Times. The idea is the Earth is going to survive. We may not, right? It's going to be human civilization, which depends on the Earth, which may not be able to survive. The Earth is not a furry bunny. The Earth is literally a god in some sense, right? It is there's a reason why people worship the Earth as a god. It harnesses cosmic powers. By what I mean is solar energy. The amount of solar energy it marshals every day is tremendous. And all we have to do is tweak it just a little bit from the conditions we found it in, and it'll brush us off like fleas on a dog, to quote George Carlin. Okay, so like, it's not that we have to save the Earth. We need to sort of be like in awe of the Earth, and in some sense, terror of pushing the planet past the conditions that we were very comfortable with. And at the same time, we have to care about life. We, the ecological hooliganism that we've been propagating is indicative of the fact that we're just not paying attention. Okay, so what are we trying to sustain? Really what we're trying to sustain are a very particular set of climatic conditions that are amenable to a particular kind of civilization, ours, technological, energy intensive, with a fairly high population, right? Because we should definitely bring our population down, but we don't want it to happen super fast because that means, mass death, and we don't want that. And we also want a maximum well-being, right? We want to maximize human well-being. So what we're saying is we want to hold the Holocene. We're trying to sort of keep the Earth in some kind of version of the Holocene in perpetuity, as long as we're around, which is interesting because we're kind of overdue for Ice Age. And if we continue the way we're going, even if we are successfully manage the Anthropocene, we're going to hold an Ice Age at bay, perhaps forever. What is the moral imperative of that? There would have been species that would have evolved in that Ice Age if we weren't around, that we're holding off. So that's why we have to sort of think now about our role on the planet in a new way. We can't just sort of have this this sort of view of nature that it's perfect on its own, and somehow we're a plague on it, because that's not really what has happened if you look at the evolutionary history of life in the planet. So this is why what I mean here is the importance of narrative, right? I have been showing people this plot of temperature and CO2 increase for years. And, this is going back 1,000 years, and you see that the temperature was relatively lower up until just recently, and now it's shooting up, right? This is data. And I could show this to people for the rest of my life, and some people would agree, but lots of people would be like, they wouldn't care. They've already made up their minds for whatever reason that this is a hoax, this is not true. And that's because most people don't understand themselves and their lives through data. They understand it through stories. And what we need is a different story about climate change, about human beings and climate change and the Anthropocene. And that's what I think this 10,000 light year perspective offers. So what we need are the right questions and the right story. So let me tell you what is the wrong story, which I think has dominated our understanding of climate change for the last 30 years. We're a plague on the planet, which has to be saved from us, right? You hear this all the time. Human beings are terrible. We're a virus. The Earth can't wait to get rid of us. And I think that is just, first of all, that is a completely self-defeating story. You tell people that and nobody wants to do anything, right? A better story is what the biosphere is doing right now, right? The Earth has run many, many experiments. For a while, the Earth was like, hey, dinosaurs, great idea. Let's see what happens. And then it was like, grasses, hey, prairie lands. Let's see what happens with prairie lands. The Earth has just run these experiments and watched what happened. A technological civilization is what's happening now. And if we screw up, the Earth will be happy to get rid of us and go on to the next experiment, right? We're not a plague. We're not something evil. We are basically the current experiment. And if we don't get it right, the Earth will move on without us. The wrong question that that we've been asking is, I have to go out and explain to people, did we change the climate? Oh, we didn't change the climate. That's a lie. That's scientists just say that. Where if you take the astrobiology of the Anthropocene, the right question is like, hey man, we built a giant world-girdling civilization. What else did you expect to happen? Of course we changed the climate, right? I mean, we're harvesting huge amounts of energy. There's no way out of changing the climate. Okay, we should have, aliens could have landed, in ancient Rome, looked around and been like, you guys are going to change your climate in about 1,000 years, right? So, the right question is to phrase climate change in a way that understands how life and planets interact. So this comes to now people can get really angry from this, but let me say this carefully. Climate change is not our fault. And what do I mean by this, right? We triggered climate change by figuring out how to harvest a particular kind of energy, right? This was fossil fuels, right? Now, we didn't do this because we're evil and we're a virus. We were doing what we'd always done, which was find ways to harvest energy for civilization building. So it's not like we found oil in the 1880s and like rubbed our hands together and we're like, ha, 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 I will change the planet with this. You know, it was a mistake driven by the adoption of a particular mode of energy harvesting. So we didn't do it with malice in our hearts. However, now that we know, not doing something about it would be a failure of the species, okay? So the astrobiological perspective, and I'm almost done here, will tell us is that Anthropocenes may not be rare. Triggering an Anthropocene probably marks a transition both for the civilization and the planet. In some sense now, we are cosmic teenagers, right? Every parent who's listening to me knows that horrible moment when you got to give your kids the keys to the car, right? And that's when you learn, you know, no matter what religion you're part of, even no religion, you start praying then. Because what what we recognize is that adolescence is a dangerous phase that every human being goes through, and that, hopefully the adolescent acquires the wisdom and the maturity to drive that car responsibly, right? So as R. Pierre Humbert says, a climate scientist, climate change is humanity's final exam. So we are teenagers entering into this very dangerous phase, which hopefully we make it through. Okay, so climate change doesn't have to be a story of villains and heroes, meaning humanity being villains, though there are definitely now some villains to this story. But what it could be is a story of right action and skillful means, to use a Buddhist term. It could be a story about maturing, okay? So, what sustainability and may look like is us finding a way to work with the biosphere so that all boats rise, that the civilization and the biosphere become more diverse, more productive, etc. Okay, so to conclude here, really climate change is the end of our childhood. We have to learn that planets have rules and we have to learn them. Sustainability, what it's probably going to mean is a planet in some sense where the civilization has awakened to its role as a planetary steward so that the biosphere and the civilization can flourish in entirely new ways. And in some sense, it's a completion of Gaia. Remember I said that one of the reasons people pushed back against Gaia theory was they thought that it had teleology in it, right? Nature doesn't have a goal. Yeah, well, we do. Once a civilization appears on your planet, if the life on a planet evolves a technological civilization, now there's teleology because we can have goals. And so in some sense, we become the mind of Gaia, and by directing it in a direction that's good for everyone. Okay, so people often, I'll conclude with this, people often ask me, do I have hope? Am I optimistic? And I always say yes, because A, what's the alternative? But B, it's because of the generation that's coming up right now. So this is a picture I took when Bill Nye the Science Guy came to the University of Rochester, and all these kids came to see Bill Nye, and all he talked about was climate change and how it was going to be this generation that moved us on to build a more just, equitable, and sustainable world. And look, these kids are ready to go. Any students who are listening to me, they are ready to go. This is a solvable problem. It is eminently solvable. And if we make it through, we're going to end up with a very different kind of civilization, and one that could be better for everything, all living things on the planet. So I will end there with hope and optimism, and I will say thank you very much.
Thank you so much, Dr. Frank. We have some questions already in the Q&A. I don't know if you can see them yourself, but I thought I'd start with the first one and invite anyone else.
That would be helpful.
Yeah, so the first question is, how do LED lights negatively affect astronomical observation? In efforts to reduce carbon, the impact of too much light may impact our natural environment.
Well, that's true. I mean, already, it is so sad that we've lost the night sky. I mean, how many people actually have the experience of seeing the Milky Way, right? Because most, even suburban areas, there's so much light pollution, as they say, that we lose the night sky. So it's absolutely true that not only any kind of lighting, there's just ambient light can really make it difficult for astronomers to do their work. But more so, we lose a kind of a fundamental piece of our heritage in terms of the night sky. So yeah, I mean, I've seen lots of proposals. We do not need to light our environments the way we do. There's ways of really reducing that overhead, how much light bounces around. And that may be, and it's a lot of wasted energy as well. So that may be part of a sustainable future of sort of rethinking how much energy we spend and where we put that energy in our lighting.
Thank you for that answer. A second question, considering how we have altered our planet, wouldn't that indicate that more technologically advanced civilization would be easier to detect, like the way our planet emits light?
Yes, actually. And so when so I'm active in a research project funded by NASA to study technosignatures. So what is happening now, and this is what I was alluding to before, now that we know exactly where to look, right? Now that we have these, we know where these planets are, where the planets in the right place for life to form are, as we build bigger and bigger telescopes, we're going to stare at those planets, and we're looking for what we call biosignatures, signatures in the atmosphere of the fact that there's a robust biosphere there, things like oxygen in the atmosphere. And these will be, we call them biosignatures because they will be signatures of the fact that there is there's a vibrant life, ecosystems happening on that planet. At the same time, you can also look for technosignatures. You don't have to wait for some civilization to try and beam you, messages saying, oh, we're here, which who knows whether they do that or not. Instead, you can look for signatures of the activity of a civilization on a planet, whether they're trying to be known or not. And so things like even city lights within 1 or 2 generations of telescopes, we will have the ability to actually perhaps detect in a rather unresolved way, city lights or factories or the heat produced by large industrial centers. So we are on the cusp. That's what I'm saying. In the next 10, 20, 30, 40 years, with the students in this audience, by the time you guys are in middle age, when your kids are going to school, we will have data relevant to both biosignatures and technosignatures. I don't know what it's going to tell us, but this is going to be the first time in the entire history of human life where we're actually going to go from just yelling at each other about our opinions about life on other worlds to actually having data.
It's really, really exciting. And a third question, in the model you studied, what differences in inputs determined which of the 3 types of outcomes, collapse, die-off, and sustainable, resulted?
That is a really excellent question, right? Because every model, as some of your students will know who've played with models, every mathematical model has parameters, knobs that you can twist to change aspects of how the interaction between the planet and the civilization would evolve. So one of the important ones was what is called climate sensitivity. So climate sensitivity is a well-known term from climate science. And the idea is if I double the amount of CO2 in the atmosphere, how much does the temperature go up, right? So depending on the conditions on the planet, where the planet is relative in its orbit, how close to the star it is or how far away it is, what the chemical composition of the planet is, that will change the climate sensitivity. And that had a lot to do with it. If the climate sensitivity was relatively high, then by a small increase in the population, which meant an increase in CO2, because there was a certain amount of CO2 per alien baby, that could really push the planet over the edge into a runaway greenhouse effect very quickly. Whereas if the sensitivity was lower, then you might be able to get through it. So the problem is we had like 5 different knobs. So knowing exactly which ones were the main cause, that required what's called a sensitivity study, which is an ongoing something we're doing now.
Thank you so much, Dr. Frank. I'm going to sneak in a question myself here before we see if there's one final one from the audience, which is about metaphor, because I was admiring, and particularly as the parent of young children, that cosmic teenager and the giving the keys to the car. And clearly metaphor is an important part of how you work as a scientist who's a communicator. We have science communication students here at SUNY Geneseo, and it's something that's very important to our science colleagues and students. So I just wonder if you'd talk a little bit about the importance of sort of metaphor and that kind of approach to science communication.
It's essential. I was very lucky in my career as a science writer. So, I grew up, I always knew I wanted to do science. When I was 5 years old, I fell in love with astronomy, and I knew that was what I was going to do. But I was profoundly impacted by Carl Sagan, who wrote these beautiful science, popular science books. And at the time, there weren't many people who did that, and it was looked down upon by many people, many other scientists. But he wrote these beautiful books about science, and he was very knowledgeable about history and culture, and he would bring those stories into his writing. And so I always knew I wanted to be a science communicator, science writer. And in graduate school, based on an argument I got into with a friend we got into an argument of whether or not physics was a language, whether theoretical physics was a language. And he happened to have worked at the Exploratorium, which is a wonderful science museum in San Francisco. And they had a magazine for the museum, and they would put out a regular call for stories, and so based on this, I submitted an idea for a story, and the person who edited it was Casey Cole, who was one of the great American science writers. She had some connection there. She was guest editing, and she taught me, the importance of metaphor, her capacities to pull the right metaphor out of the details of the science and deploy that, so to speak, to foster an understanding in the reader was essential. I mean, it was so powerful and made her such a great writer that I really learned, finding the right metaphor, using it, nurturing it was absolutely crucial. And in this case, my argument is that we've had the wrong metaphor when we talk about climate change. Almost always when people talk about climate change, the metaphor is a virus. Human beings are a virus on the planet. And that doesn't help anybody. Like, that just doesn't, first of all, I think it's wrong, but also you're not going to be, you need to motivate collective action. And collective action requires a good story that will gather people around it. And a good story, as you know, requires good metaphors. So a better metaphor is this idea of the cosmic teenager. A better metaphor is to look at what we're doing and say, we're not a virus, we're actually we're a success story. We're a planetary success story. Look, we went from being a bunch of, hairless monkeys, hairless apes, to actually, controlling the planet's dynamics. And so, we could end here, but if we want to continue as a success story, then we need to come in harmony with the planet.
Thank you. I'm going to give you the final two questions at once because I think they speak to one another, but hoping I'm not giving you too much to juggle. But one of them is, in your opinion, what is the path to sustainability? And the other one from one of our students is, do you believe there are planets out there whose planetary patterns are similar to Earth that possibly give us the solution to climate change?
Oh, those are great questions. All right, so first of all, what is the path to sustainability? That path is a really fundamental reorganization of our understanding about what we are on the planet, right? We have in our myths, especially the myths of the dominant culture on the planet, the culture that produced the Industrial Revolution, that the understanding of the relationship between human beings and the planet is one of domination. Right? Human beings are the highest form of life, and we're, everything we see is ours to control and dominate. And that is a fundamental misconception, as we've seen. Instead, there are other myths from other cultures, particularly hunter-gatherers, indigenous cultures, that understood that we were just one part of this, this web of this tapestry of life on the planet. We're not on top. And that's my point about the fact, speaking of metaphors, that the Earth, we need to remind ourselves that the Earth is a god, right? An angry god. You don't want to be around when the god gets angry. So we need to reintegrate ourselves into the functioning of the biosphere. And so that means it's a different understanding of the science of living things and the biosphere, that that things are a networked whole. So there's all kinds of really rich, beautiful science that goes along with this. But also it requires reorganizing society in some sense, that the aspects, the consumerism, the aspects of our culture that's just like, devour every resource, that can't continue. This is a finite planet. And I'll note that, it's not just Western culture that did this. Almost every empire which is, most of human history has been one empire after the other. None of them were, very good about resources. Everybody was kind of into resource extraction and consumed as much as they possibly could. Our culture just got really good at it, really effective at it. So there needs to be some kind of reorganization in, sort of how we consume, how, wealth, and how wealth is distributed and what wealth is used for. So, and the second question was, could we learn from other planets? I think probably by the time we really get other planets to see, it'll be, we're going to have to do this for ourselves, right? I think we can use other planets and other civilizations as a metaphor, or to do the kinds of theoretical studies to imagine other types of histories that'll help us see what our history has to be. But we really, I mean, we got to make this change now, right? The transition we need to make is over the next 50 years. And I doubt that we're going to see another civilization with as much clarity, with as much resolution, that will actually see the solution to our problems. Long term, though, over 100 or more years, I think we will get, I hope we will get other examples of civilizations that can teach us some really interesting things.
With thanks then to Dr. Frank for a really stirring and enlightening, pun fully intended, talk. I want to, we can't give you a warm Geneseo thanks in person, but we can over Zoom, and a deep gratitude to you for that talk, and for its optimism and hope, as well as its urgency. As we end today's keynote presentation, I want to give my thanks to Jack and Carol Kramer for their lovely words introducing Dr. Frank, and to Dr. Battles for her thoughtful introduction to Great Day's keynote speech and the Kramers. Great Day, this year 5 great days, would not be possible without the tenacious efforts of a wonderful group of people who make it so make it available. Our PDF program has a full list of acknowledgements, but I want to pause to thank particularly Anne Baldwin, Adam Klingers, and Jonathan Grunert, who have been tireless behind the scenes. And I want to thank to our creative and ever-willing Great Day intern team, Paige Klosser, Leah Wertzman, Taryn Franciosa, and Alexis Daresh. And finally, Great Day can only exist thanks to the amazing work produced by students on this wonderful campus, and thanks to the faculty and staff who go the extra mile or 10 to mentor students and help them prepare work for sharing. So our gratitude goes especially to the participants and their mentors. And if you have time to show that gratitude in page views, please head over to the virtual app to see the really exciting work that is being produced even in, and especially because of, these challenging times. With a final thank you to Dr. Frank, good afternoon to everyone, and thanks for being here.
Thank you.